Hello everyone, my name is Icey from Imperial College London. I'm glad to present my work via this video in this special situation. In this video, I'm going to present the proposed soft fingertip and its applications for precise in-hand manipulations and others. I will go through several key elements in this paper in this order. So, before we move to this new type of soft fingertip, I'm going to give you a general background of soft fingertips in robot hand design area. Soft fingertips have shown significant development for grasping tasks due to their high compliance characteristics. For example, this well-known granular jamming universal gripper made by Armand can easily adapt to the shape of objects. For grasping soft objects, soft fingertips with tactile sensors perform better than rigid fingertips. With rigid fingertips, robotic grippers can achieve a repeatable, stable grasping force and high precision control, but their lack of adaptability and compliance, and they are prone to damage and deform very fragile and soft objects. Apart from the grasping tasks, here are some other applications of soft fingertips. Figure 3 shows that the granular jamming soft fingertips have been attached to a simple gripper to perform manipulation tasks. Figure 4 shows the soft compliance capability being used in tactile sensor applications. While soft fingertips have shown significant development for grasping tasks, its ability to facilitate the manipulation of objects within the hand is still limited. In this paper, we propose this novel soft fingertip design for in-hand manipulating soft objects via embedded air cavities. For each soft fingertip, it consists of 2 air cavities inside, which can perform as tactile sensors and achieve active shape changing when the air cavity is inflated with air via positive pressure. Those are the prototype of the soft fingertips, where the 2 embedded red air cavities made from silicone are evenly distributed in each fingertip under the semi-transparent silicone rubber. The special finger-based structure is designed to secure the silicone fingertip and the air, and ensure the inflate direction is going as desired. Now I'm going to show you some demos of the dual functional soft fingertips. Here we use the embedded air cavity as soft tactile sensors. According to the ideal gas law, the internal air pressure shows a correlation to the volume change of the air cavity. Considering the incompressibility of silicone, the volume change of the air cavity caused by external force can be measured with a pressure sensor. This video illustrates the active deformation of the fingertip via positive pressure. Here, the internal pressure of the air cavity starts from 0 kPa to 60 kPa. This active deformation can secure the grasp in vertical direction without escaping and damaging the soft objects. In order to understand the fingertip properly, we perform the fingertip characterization test to analyze the relationship between the pressure and the deformation. This video shows the numerical deformation of the fingertip based on the image processing of a real inflated and deflated fingertip on various pressure levels shown in different color. And based on the outline curves, we define the best fit equation in MATLAB. Here, y is the deformation, x is the point along the edge of the fingertip in 2D, and p is the internal pressure. Later on, we used the previous defined equation to generate the simulation model for in-hand translation and rotation. The control algorithm for this manipulation is described in the next two slides. For translation tasks, both air cavities of left fingertip are inflated for moving right. Both air cavities of right fingertip are inflated for opposite translation direction. For this simulation model, the object translation distance t is determined from the object center point distance between the initial stage and the final stage, where the variable is the pressure P. When the left top and right bottom air cavities are inflated together, the grasped object rotates clockwise. Instead, if the left bottom and right top air cavities are inflated together, the grasped object rotates anti-clockwise. For the simulation model, we assume the contact points between the non-inflated air cavities and the object stay the same, and then the rotation angle R can be worked out by trigonometry. Here is the insight of the internal pressure of the soft fingertip during the in-hand manipulation. Different color indicates different air cavities. Apart from the active deformed air cavities, the rest of the finger is acting as an active tactile sensor to ensure the contact forces between fingertip and soft objects are constant during manipulation by actuating the servo motor. As you can see in the bottom right figure, this light blue curve indicates the finger interval, where it is increasing during the manipulation. Additionally, the object internal pressure in green is stable during the manipulation, which means the object was not being compressed during the manipulation. The aim of this experiment is to show the dual-purpose soft fingertip can perform precise in-hand manipulation of soft objects with a limited dexterity gripper. The proposed fingertip is attached to the fingers of a redesigned GR2 gripper. Here is an example of GR2 gripper manipulates rigid objects with normal fingertips. In the experiment, we have tested the gripper at 7 different positions. Those 7 grasping positions are distributed evenly in the GR2 movement range, shown as blue dots, where position 4 is the middle grasping position. 1 and 7 are the maximum left and right grasping position, respectively. Previously, we have seen the performance of the gripper at the middle grasping position. At those 7 testing positions, the initial grasping angle are different as shown in the video. Here, black arrows show the object initial rotation due to gripper design and rolling. The table shows the exact values of rotation. Negative signs means rotating in anti-clockwise direction. This video demonstrates the gripper performance at different grasping phase. The green shaded areas illustrate the experimental rotation range at different grasping positions. Similarly, pink shaded area indicates the translation range. The translation and rotation capabilities of the gripper with the dual-purpose fingertips has been shown clearly. We observed that the relative position between the fingertip and the object affect the in-hand manipulation performance, and both translation and rotation range decrease when the initial rotation angle of the object increase. In a rotation task, if the object has initial rotation stage in the same direction of the target rotation, For example, if the object is held in at position 6 and intended to rotate to right, the inflated ear cavities will have a gap between the grasping object. During the inflating stage, the ear cavity will touch the object first and then rotate the object. Therefore, in this case, the object rotation is smaller than normal. Here is the summary of this paper. This work proposed and evaluated a novel dual-purpose soft fingertip design, presenting a new way to precisely in-hand manipulate soft objects without damaging. This approach is based on enhancing the dexterity of rubber hands via soft fingertips with tactile sensing and active shape changing. With active shape changing of the embedded ear cavities, the fingertip has proved its ability to in-hand manipulate soft objects prehensively with pressure feedback control. The proposed simulation model gives an evaluation on the manipulation ability of the enhanced gripper, which can be improved by taking the initial rotation angle and the deformation of the fingertips into account. With the proposed closed-loop control approach and the novel dual-purpose fingertip, the object position can be adjusted at each grasping configuration, thus increasing largely the gripper's dexterity. The control algorithm can be developed further in future works for more complex prehensile in-hand manipulations that combine translation and rotations with irregular objects. And that's it. Thanks for listening. Bye.